Section 5.4 covers the fundamental theorem of calculus, particularly part 1 of the fundamental theorem of calculus. The evaluation theorem that we went over in 5.3 is the fundamental theorem of calculus part 2. So the fundamental theorem of calculus, I'm going to probably call it the FTOC, right? It is more theoretical than the evaluation theorem. So we'll do our best to make sense of this theory. So part 1 says if f is a continuous function on the interval a to b. Right, so here is a continuous function. No holes, no asymptotes, no jumps. Okay, then g of x is defined to be the integral from a to x of this f function. So g of x is defined to be the area under the curve of f from a to x. Right? So if we had a continuous function from a to b, and we were looking at just the area from a to x. So x has to be somewhere between a and b. So if x was like here, then g of x would return the area below f between a and x. All right, so it's the area between a and x of the f function. So the next part here, okay, that says that is g prime of x is equal to f of x, right? So if we were to differentiate both of these sides, right, we get g prime of x on the left, and when you differentiate an integral, you get the original function back out. Now, why does it change from t to x? Okay, what happens to these upper bound and lower bound? I'll show you a proof in just a moment, okay, about why that happens, right? But I want you to think about g of x is called an area so far function. So if we wanted to find the area from a to some point x, we can move that x as far away from a or as close to a as we want, but it's just an area between the lower bound and x, all right? So I have drawn a function here. This is the f of t. Okay, so these are t values here. So from 0 to 1, this is just a linear function, straight line. Okay, from 1 to 2, this is a horizontal line. And then from 2 to 5, we have this curved function here. Okay, so since we're going to let g of x be the integral from 0 to x of f of t, I just want to demonstrate what the area so far means. Okay, so if they asked us, part 1, calculate g of 0. Right, so just like in number or in function notation, we're replacing the x with 0. So we're looking at the integral from 0 to 0 now, right? So this, if we replace x with 0, we're looking at the integral from 0 to 0, right? So from 0 to 0, there is no area there, okay? We're not moving, so this area is simply 0. If we were to calculate g of 1, right? What is the area under the curve f of t from 0 to 1? So we're moving that x value farther away from 0. So we can use geometry here to evaluate this limit. So from 0 to 1, we're getting the area here, which is a triangle. Okay, so this area is going to be 1/2 the base times the height. So 1/2 the base of this triangle is 1. The height of this triangle is 2. So we're going to get 1/2 of 2, which is 1. All right. So the area from 0 to 1 is 1. Right? What's g of 2? Okay. So now we're moving the x value a little bit farther away, and we're going to look at the integral from 0 to 2. Right? Again, if I ask for g of 2, we're replacing this x with 2, and now we want the area from 0 to 2 of our curve. Right? So from 0 to 2, we are going to add to the area of the triangle the area of this rectangle. Right? So the area of the rectangle, base times height, the area of this rectangle is 2. Right? The area of the triangle was 1. We could do 1 plus 2 is now 3. Okay? Because we're doing the area from 0 to 1 plus the area from 1 to 2. And if you didn't realize, we can do that in integral notation, right? So the integral from 0 to 2, we could split that up. The integral of 0 to 1 plus the integral from 1 to 2. Okay, and in terms of area on this function, it should make sense. Right, I want to do just one more. Let's find g of 4. Okay, so we're going to look at the area under the f function from 0 to 4. Now, we know the area from 1 to 2, or I'm sorry, from 0 to 2, right? The area from 0 to 2 is 3, okay? So we're adding on to it the area above the curve here and below the curve here. So I'm going to draw a line here, okay? And so this area, not so easy to configure. We could kind of guesstimate what we think it is. But what I want you to realize is that the area above the x-axis is counted as positive, and the area below the x-axis is counted as negative. And I know my drawing is a little bad here, but it really is meant to be symmetrical. Okay, the area above from 2 to 3 here is supposed to be the same area as the area from 3 to 4 that's below the x-axis. So when we go up from 0 to 4, we're adding a net area of 0, okay, if these were equal. And so let's split this up, okay? Let's go the area from 0 to 2 plus the area from 2 to 3 plus the area from 3 to 4, okay? And so the area from 0 to 2 is 3 plus, now no matter what value we give here, I'm going to give about 1.5. And the reason why I'm going to give 1.5 is because if I were to kind of draw some grid lines here, I almost have a whole rectangle here, or a whole square here, and I have half of a square here. And so I'm going to call this 1.5, right? So if the area from 2 to 3 is positive 1.5, then the area from 3 to 4 would be negative 1.5, which is the net area of 0, right? And so we get a final area of 3, right? So it's an area so far, okay? We're just finding the value of the area below the f function, right? So let's go ahead and talk about why is g prime of x equal to f of x, right? So just a little semi-quasi proof for you here. So let's let g of x be the area from 0 to x, f of t dt. Okay. So, and actually, you know what? Let me make not just 0 here. Let's put a constant here. Okay. Just like the definition, right? Because g of x was the area from a to x. So if I were to calculate this integral, I would have to find the antiderivative of f. And for simplicity's sake, I'm going to call the antiderivative of little f capital F. All right. So I want to evaluate the antiderivative from a to x. All right. So the way we do that using the evaluation theorem is we plug in the upper limit into the antiderivative, and then we subtract from that the lower limit plugged into the antiderivative. Okay, so now we have g of x equals capital F of x minus capital F of a. All right, so let me write that down here. All right, so what I want to show you is that g prime is really little f prime. All right, so what I'm going to do is I'm going to differentiate this side, and I'm going to differentiate this side. All right, so the derivative of g we'll just call g prime of x. All right, and the derivative of capital F of x. Okay, the derivative of the antiderivative should get you back to the original, but see we've evaluated the antiderivative x now. We've replaced all the t's with x's. So we're going to get little f of x here. All right? And then the antiderivative evaluated at a is a constant. And what happens to constants is that they go to 0. Okay? So here I have what we were trying to prove. And that is that g prime of x equals the original function, okay, little f of x. So not little f of t, but little f of x, because when we integrate, we're plugging the upper bound into the antiderivative. All right, so it is very theoretical. It may seem like I'm waving my hands a little bit too much, but it really is this simple, okay? You take the antiderivative evaluated at x minus the antiderivative evaluated at a. A needs to be a constant, right? The derivative, the antiderivative gets you back to the original function, all right? And then we have that the derivative equals little f. All right, so I have some problems to work through with you, all right? So let's let g of x equal the integral from a to x of f of t dt. We're going to let a equal 1, and we're going to let f of t equal t cubed. All right, so the directions say find a formula for g of x and calculate g prime of x. So if we were to find a formula for g of x, we're just going to make these substitutions. Okay, a is 1, f of t is t cubed. So now g of x is equal to the integral from 1 to x of t cubed dt. All right. Now, I'm not going to do the shortcut right away. All right. Let's go ahead and work this out because we know what the antiderivative of t cubed is. Right. So the antiderivative of t cubed is going to be 1 power higher. So we're going to get t to the 4th, right? And so when I differentiate this, 4 times what would get me a coefficient of 1, right? Because I want, if I differentiate this, I'm going to get 4t cubed, and I don't want 4t cubed, I want just 1t cubed. So if I put a 1/4 as a coefficient here, then the derivative of 1/4 t to the 4th is 1t cubed. All right, so here's my antiderivative, and we're going to evaluate that from 1 to x. All right, so if I plug the upper limit into this, we're going to get 1/4 x to the fourth minus, plug the lower limit into that, we're going to get just 1/4. All right, so now I have a formula for g of x, right? G of x as a formula is going to be 1/4 x to the fourth minus 1/4. All right, this is my formula for the area so far function. So if I wanted to know the area under t cubed from 1 to 5, I could plug 5 into this function and get it, right? So this is my area under the curve of t cubed, right? But the directions also say calculate g prime of x. So let's go ahead and do that, right? So g prime of x, if I differentiate the left-hand side, I have to differentiate the right-hand side. And so when I take the derivative of the right-hand side, I'm going to get 4 times 1/4, which is 1. And then I need to subtract 1 from the power, so I'm just going to get x cubed, right? And then when I differentiate a constant, it goes away. So g prime of x equals x cubed, right? So what I want you to realize here is that g prime of x is equal to, if f of t is t cubed, then f of x is x cubed, right? So g prime of x equals the original function evaluated at x, right? We just showed another reason why g prime of x equals f of x, right? So we're integrating with respect to t, but if we take the derivative, the t goes away because we're plugging in that upper bound into the antiderivative, and it changes that variable to f of x, right? Because if f of t is t cubed, then f of x is x cubed, right? So we just showed that g prime of x equals little f of x, right? I want to do just a few more. I got some homework pulled up here. All right, so they want us to find the derivative of the function. And so the function is going to be g of x equals integral from 3 to x e to the t squared minus t dt. So this one just wants us to find g prime of x, right? And it's going to equal f of x, right? So quite simply, we're going to get, if I take the derivative of an integral, it cancels, right? But we're going to get the antiderivative evaluated at x minus the antiderivative evaluated at 3. Can I write like this? Right? So if I take the derivative of what this integral equals, so we're going to differentiate f of x minus f of 3, right? Because the derivative of g is equal to the derivative of this. And so I get the derivative of g is equal to, the derivative, the antiderivative is back to the original function. And the derivative of a constant is 0. And so little f of x is going to be equal to little f of the little f function, not evaluated at t, but evaluated at x, right? So this means that g prime of x is equal to e to the x squared minus x, right? Plus a constant, if you will, right? Actually, I don't need the constant because it went to 0. Okay. So, I mean, on face value, it looks like we're just taking this function and plugging x in it, and that is true, all right? But there has to be a constant on the bottom, and it has to be x on top. So let me just do one more with you, okay? And then I'll show you a little bit different. I couldn't see where I was writing. Sorry, guys. Okay, so let's look at this function. G of y equals the integral from 2 to y of t squared sine t dt. So I really want you to realize that little f of t is t squared sine t. Right? So if I take the derivative of both sides here, right? Actually, let me do this. Without finding what the actual antiderivative is, we're just going to call it f of t. And we're going to evaluate it from 2 to y, right? So the antiderivative evaluated from 2 to y looks like capital F of y minus capital F of 2, right? So now I have little g of y equals the antiderivative at y minus the antiderivative at 2. And so the directions still say find the derivative of this function, right? So I'm going to differentiate. So the derivative of g of y is g prime of y. The derivative of the antiderivative gets us back to the original function. It's going to get us back to little f of y, all right? And then the derivative of this constant is going to be 0. So what is little f evaluated at y? Little f evaluated at y is a y plugged into this function here, y squared sine y. Okay, so it's very theoretical. Without actually finding the antiderivative, we're taking the derivative of our antiderivative. All right, now I mentioned that the bottom number needs to be the constant, the top number needs to be the variable. Okay, so what happens when that switches? Okay. Oh, I got rid of my video. Okay, let me pull up another homework question that does that. And so yeah, let's look at capital F of x is the integral from x to pi square root of 1 plus secant t dt. All right, so instead of the derivative being from a to x, now it's x to a, if you will, right? So we can still use this pattern here, right? And so what we're going to do is we're not actually going to find the antiderivative. We're just going to call it capital F. Now I know this is capital F too, but remember, little f of t is the square root of 1 plus secant t. Okay, so I'm going to get capital, let's take the antiderivative here. And so we're going to get the antiderivative evaluated from x to pi. Right? So this is equal to the antiderivative at pi minus the antiderivative at x. Right? Let me call this capital G, because I like my antiderivatives to be capital F. Right? So let's not do that. Okay, let's call it capital G. So now I have capital G of x, the area function, is equal to the antiderivative at pi minus the antiderivative at x. And we always want to find what the derivative of g of x is, right? So it's always going to say find g prime of x, right? So we want to differentiate this equation here. So we're going to get g prime of x equals. Now, the antiderivative evaluated at pi is just a constant, so this is going to go to 0. Okay, all of this goes to 0. And then the derivative, the antiderivative, gets us back to little f. So we're going to get minus little f of x, right? So what is little f of x? Well, if little f of t is the square root of 1 plus secant t, little f of x is the square root of 1 plus secant x. So I get g prime of x equals negative the square root of 1 plus secant t. Right. If you keep going in this manner, you don't have to remember all those rules of integrals, but let me just give it to you just in case you're like, she didn't show us that. Okay, so if we had an integral from a to b of some function, okay, and for instance, if we wanted to change the upper and the lower bound, we could do that by throwing a negative in front. So that's equal to the negative integral of b to a f of x dx. So if you did like view an example of this problem, what they would do is they would switch the order here, put the pi on the bottom and the x on the top, but they would throw a negative out in front. And so you end up getting negative the f of x first and the constant second, but you still get negative f of x. All right, so this method still holds without even showing you that this is true. All right. But it is, okay? So what I'd like to show you now, okay, is yet another variation of this problem, okay? So let's let g of x be the integral from 1 to x to the 4th secant squared t dt, right? So we do have the constant on the bottom, but we have an x to the 4th on top, right? And just to remind you, right, little f of t is secant squared of t, right? So what I would like to do, though, is to use the same method, okay? Without actually finding what the antiderivative is, let's just call it capital F. So this is going to equal the antiderivative evaluated from 1 to x to the 4th now, right? So we're going to get, if I plug x to the 4th in there, we're going to get the antiderivative evaluated x to the 4th minus the antiderivative evaluated at 1, right? So that's what g of x equals. Okay, capital F of x to the 4th minus capital F of 1. But we want to find g prime of x, and so I'm going to differentiate this. Okay. So now when we differentiate, we're going to get g prime of x equals, here, the derivative of capital F of x to the 4th. This really is a chain rule, okay, where the outside function is capital F, and the inside function is x to the 4th. So if I differentiate capital F of x to the 4th, I need to use the chain rule here. So the derivative of the outside, the derivative of the antiderivative gets us back to the original. And then the derivative inside function is 4x cubed, right? So if I plug b into a prime, multiply times b prime, I'm going to switch over here. Okay. I get g prime of x equals x to the 4th plugged into little f times 4x cubed, right? That's the derivative of capital F of x to the 4th. And then the antiderivative evaluated at 1 is a constant, and so when we differentiate, we're going to get 0 here, right? So if I were to find a formula for g prime of x, I want to take my little f function, plug x to the 4th in that, and then multiply times 4x cubed. So I'm going to get secant squared of x to the fourth times 4x cubed. Right? It's a chain rule. Okay? When you evaluate the antiderivative, something other than x, when you differentiate that, you have to remember to use the chain rule. Okay? So let me do a few more like that. Okay? So let me pull up the homework here real quick. Yeah, good one. I know you probably can't see what I'm doing, but let me just write it down and then I'll get the screen moved where you can see it. So let's go 0 to x squared. One plus r cubed dr. Okay, so I have h of x equals the integral from 0 to x squared of the square root of 1 plus r cubed dr. So we have a little f of r, if you will, which is 1 plus r cubed. Okay. But let's go ahead and evaluate this integral. Okay. Theoretically, without finding the antiderivative, let's just call it capital F. Okay. So we're going to get the antiderivative of capital F, and we're going to evaluate that from 0 to x squared. Okay. So if I do that, then I'm going to get the capital F function of x squared minus the antiderivative of capital F evaluated at 0. Okay, so this is what h of x equals now. And if I were to differentiate this, then I get h prime of x equals, notice this is another chain rule. Okay, so I'm going to get the outside function is the antiderivative function. And it doesn't really matter what variable you use there. We're going to replace it. So I almost always use x, right? The inside function is x squared. So if I were to take the derivative of both the outside and the inside, the derivative of the antiderivative is little f, okay? And the derivative of x squared is 2x. So in order to differentiate this, I'm going to plug b into a prime, multiply times b prime. I should have wrote h prime so soon. All right, so I'm going to do the chain rule here. Plug x squared into little f. So I'm going to get little f of x squared, but I need to multiply it times b prime, which is 2x. And then the antiderivative evaluated at 0 is a constant, and the derivative constant is 0. So I get a formula for the derivative of h of x is the little f function evaluated at x squared times 2x. And the little f function evaluated at x squared, we'll plug an x squared in here. So I'm going to get the square root of 1 plus x squared cubed times 2x. Right? So one more simplification step. If we cube x squared, we multiply the power, so we get x to the 6th, and this is multiplied times 2x. Right? So the antiderivative form always works. Right? If you go ahead and do the antiderivative in general form, evaluate it from the lower limit to the upper limit, and then just remember when you have a constant in there, it goes away. And then if the upper limit is a function of x that requires the chain rule, go ahead and use the chain rule. If it's just x, then you just get little f of x. Right? And it doesn't matter really if this was x squared to 0, because if you use this method, you're going to get that negative sign in your answer just from using this technique. All right, so it works out really, really well. Okay. I have one more problem type to show you. So the directions are going to say verify by differentiation. All right, so we want to prove that this is true. Okay, we want to prove that the integral of cosine cubed x dx is equal to sine x minus 1/3 sine cubed x plus c. So when it says verify by differentiation, we just want to take the derivative of both sides. Okay, so I'm going to take the derivative of the left-hand side, and I'm going to take the derivative of the right-hand side. Right, now, believe it or not, the left-hand side is the easier side because when you differentiate an integral, these are inverse operations, and so we're just going to get cosine cubed x. All right, so the derivative of integral cancels each other out, and we get cosine cubed. Now, on the other side, we need to integrate all three of these terms. Okay, so the derivative of sine is cosine, and the derivative of 1/3 sine cubed x. This is going to require a chain rule. So I'm going to go ahead and outline the chain rule here. Now we have a constant. Okay, I'm going to leave the constant as part of the outside function. So I really, 1/3 sine cubed x is 1/3 sine x cubed, like so. So you can see that sine x is inside this cubic function. So my outside function is going to be 1/3 x cubed, and my inside function is going to be sine x. So if I take the derivative of the outside and the derivative of the inside, the derivative of the outside now is 3 times 1/3 is 1. So I'm going to get 1x squared. The derivative of the inside is cosine x. So to do the chain rule here, I need to plug b into a prime and then multiply times b prime. So I'm going to get sine x into x squared is sine squared x. And then I'm going to multiply by cosine. Okay. And then, of course, the derivative of the constant is a constant. So I have this equation now. I'm going to kind of clean it up. I have cosine x minus sine squared x cosine x. Right? And you're like, wait, I thought we were supposed to get cosine cubed. So we kind of have some trig identities to use here and simplify this. So what I want to do is I see that both terms have a cosine. Let's go ahead and factor that out. So if I factor out a cosine, I'm left with 1 minus sine squared. Right? And you should recognize 1 minus sine squared. That's the Pythagorean identity, right? Because we have sine squared x plus cosine squared x equals 1. And so if I move the sine squared over, I get cosine squared x equals 1 minus sine squared x. So 1 minus sine squared x is the same thing as cosine squared x. So now I have cosine x times cosine squared x, which is indeed cosine cubed, right? So we did prove that the left hand equals the right hand. All right, so that really does, oh, you know what? Look, I have one more really good example. Okay, let's do, I was going to conclude it, but let's go ahead and do this one more example here. So let's evaluate the integral from 1 to 2, v cubed plus 3b to the 6th over b to the 4th dv. Now, this isn't going to use the fundamental theorem of calculus part 1. This is really just an evaluation one, but it has some really good examples in it. Okay. So in order to integrate a fraction, we would have to use partial fractions, which we're not going to cover this semester. So in order to do this one, you want to split these up. Okay, you want to go ahead and divide b cubed by v to the fourth, and then divide 3v to the sixth by v to the fourth. And so when I split that numerator, I'm going to go ahead and write it as two separate integrals at the same time. So I'm going to get the integral of 1 to 2 of b cubed divided by v to the fourth, plus the integral from 1 to 2, 3v to the sixth divided by v to the fourth. Oops, and both of these are integrating with respect to v. Okay. So now what we're going to do is we're going to go ahead and reduce these. Right? So we get the integral from 1 to 2 of 1 over v dv plus the integral from 1 to 2 of 3v squared dv. Right? And I am going to leave it as 1 over v. Right? And the reason is, I mean, if you were to try to integrate v to the negative 1 using normal methods, right, we would have to add 1 to negative 1 and get 0, and then divide by 0 somehow, and you can't do that, right? And so this is not the correct way to integrate v to the negative 1. So really train yourself to see past making it a negative exponent. If it was negative 2, it'd work fine, but the negative 1 doesn't, right? So I'm going to leave it here. And so if we have a v to the negative 1 power, and we're not going to integrate using the power rule here, how do we integrate this? Well, this is really the derivative of v over v, right? Because if I had the function as v, the derivative of v would be 1. And so we really have an integral of f prime of v over f of v, if you will, right? And so what is this the derivative of? Well, it's the derivative of ln, right? And so when you have a v to the negative 1 power, you really have to think it's an ln function, okay? Because now the derivative v on top and v is on the bottom. So the antiderivative of 1 over v is ln of v. And we're going to evaluate that from 1 to 2. Okay? And then what's the antiderivative of 3v squared? Well, this we can do the power rule on. We're going to get v cubed. Okay? 3v squared is exactly what I want, so the coefficient doesn't need to be changed. We're just going to leave it at a 1, and we're going to evaluate this from 1 to 2 as well. Right? So if I go ahead and do those evaluations, we're going to get ln of 2 minus ln of 1 plus 2 cubed minus 1 cubed. And so ln of 1 is 0. You can plug it in your calculator if you don't believe me, but it is. So we're going to get ln of 2 minus 0 plus 8 minus 1. So a final answer is ln of 2 plus 7. Right? So really, really big concept here. If you have the integral of 1 over x dx, you're going to get ln of x plus c. All right? Because x to the negative 1 power doesn't work. But if you had the integral of 1 over x squared dx, you can write that as x to the negative 2 and take the antiderivative using the power rule. So we would get x to the negative 1, negative x to the negative. So I put a negative here, okay? So that when I differentiate this, I get the correct coefficient. So if I differentiate this, I get positive 1 x to the negative 2, which is what I want. All right? But if it's x to the negative 1 power, it's got to be an ln. All right. So that concludes 5.4.